Okay, so yesterday we did exponential functions. Now we got the natural exponential function. Whoa, the natural exponential function. The natural exponential function involves a number e. And the further you go in math, the more e's you're going to see. Just saying that e is a special number. E is a decimal approximation is 2.718281828459043. And I didn't put this, but it's dot, dot, dot. It's irrational. Never repeats, never terminates, never stops. Just keeps going. It's kind of like pi, except it's E. And where it comes from is this right here. It comes from this little series, 1 plus 1 over n to the nth power. As you get bigger and bigger numbers for n, as you can see what happens, you start putting numbers in for n, the bigger the numbers get, then what starts happening? They're getting closer and closer to this. And you could keep putting, and the reason it goes on forever and ever is because obviously the numbers go forever and ever. So you could keep putting bigger and bigger numbers in for your n's up here, and you're going to get more and more exact value of e, even though you can never quite get there because obviously it's irrational. All right, the natural exponential function is this right here. It's basically e to the x. Yesterday we had a to the x. We could put in any positive number we wanted to, other than 1, and we would graph it or we would find values. Today we're going to do the exact same thing we did yesterday, except everything's going to be base e. The base is going to be e today, and it is often referred to as the, not just an exponential function, but the exponential function. The graph of it, as you should expect, if you see the red graph right there, look where it is. It's in between 2 to the x and 3 to the x, which makes sense because e is, it's about 2.718. It's 2.7. So it's between 2 and 3, closer to the 3 than it is the 2, obviously. So that's what the graph looks like. The same as it did yesterday. Still passes through 1 on the y-axis. The x-axis is still an asymptote. All that stuff is exactly the same. The first thing they're going to have you do is just plug in values. We're going to use the calculator for this, obviously, because E is such a wild number. Your E button is actually located above your LN button on your calc. You'll be able to get your calculator out and make sure you can find it. It's not the letter E on your calc. It's actually above the LN button, 2 different buttons there. So if you punch in E cubed, if you punch in A, just punch in E to the 3rd power, you get 20. It says 5 decimal places, 0.8554. Do the next one, punch in 2 times e to that negative exponent, you get 1.17721. Part C, punch it in, e to the 4.8 power, 121.51042, it's a great 042. That's just flat out punching stuff in your calc. You should have no issue there, as long as you can find the button. So make sure you can find your e on your calc. Sketch the graph. Okay, first of all, let's sketch the original graph. The original graph, remember, goes through 1 right here. And really, if you put in 1, I'm actually talking about this right here. I'm actually graphing this before I graph these up here. If I put in 1, I would get like 2.718. It's about right there. So the graph of just regular e to the x would look like this. If you put a negative x in there, the negatives in the exponent means it reflects across the y-axis. So I'm going to go blue. I'm going to reflect across the y. It's still going to cross there, but the negative one's going to be up here. And it's going to look exactly the same. It's been reflected across the y, just like that. The second one here has a 3 in the front, which means it's been vertically stretched by 3. And it has a 0.5 in the x, which means it's been horizontally stretched by 2. Remember, by the reciprocal. Horizontal stretched by the reciprocal. So, wow. Let's take this original graph right here. Let's see, this, I'm going green. Okay, so this original graph is the red one. I'm going to take the red, I'm going to vertically stretch it by 3. So that point to 0.1 is now up at 0.3 because it's been stretched up there. And instead of doing this, taking this point, right, I could take that point, I guess. It's been horizontally stretched by 2. So instead of it being at 1, it's going to be way over here at 3. Let me think here. Okay, that second point, this red point right here, let me see. That one right here, I'm going to point at it. It's been vertically stretched by 3 and horizontally stretched by 2. So right now it's at 2.7. So I would do 2.7 times 3, which is going to be, let me punch it in real quick, 2.7 times 3 is going now 8.1. So it's going to be about 8.1, about here. But it's also been horizontally stretched by 2, so it's going 2 times past that. So it's going over to 2 right there. So that point right here got vertically stretched and horizontally stretched. So now if I graph that green, it's going to do this right here. Okay, so it's been horizontally stretched up, vertically stretched up and horizontally stretched wider. So that's kind of crazy to graph that one. And we'll work on those tomorrow. All right. What a problem for our day and time. An infectious disease begins to spread in a small city population 10,000. After 10 days, the number of people who have succumbed to the virus is modeled by this function. Almost all epidemics follow an exponential function like this right here, believe it or not. It says how many people are there affected initially at time 0. So to figure that out, we're just going to put 0 in for that t right there and punch it straight in the calc. So it looked like on my calculator 10,000 divided by parentheses 5 plus 1245 e, and I'm going to do the negative 0.97 times 0 is 0, which is just 1. So if you punch that in, you're going to get, let's see here, at time 0, it's going to be very close to 8, very close to 8. So I'm going to get 8. There's 8 people sick the first day. Now, after 1 day, obviously I'd put in 1 right there. After 2 days, I'd put in a 2. And after 5 days, I'd put in a 5. I'm going to, instead of showing you all that work, I'm just going to show you what happens here. When I plugged in the 1, after 1 day, 21 people. So from 8 to 21. The second day, up to 54, because it's growing exponentially. On the third day, it's all the way up to, the fifth day, we had fifth day there. The fifth day, all the way up to 678 people. Now, then it says, the bottom says graph. Now, we would graph this on the calculator, obviously. So I punched this function in on my calculator, and here's the graph that came out. And this is what happens with diseases and epidemics. Is they grow, then they just level out, okay? Eventually, like, everybody's going to gets it, so it kind of levels out. Also works with, like, stocking fish in a pond. You stock fish start reproducing, you get tons and tons of fish, but eventually the pond can't hold so many, so it just levels out, okay? So pretty cool how that happens. Exponential function there. The last thing today is continuously compounded interest. We did compound interest yesterday, where we talked about it would grow based on how many times a year it compounded, or what the rate was, how long you left it in. Same thing is true here, except it's compounded continuously. It's not going to give you like, oh, it's 3 times a year, it's quarterly, it's semi-annually, whatever. It's continuous. The formula is a little bit different. Some people call it the PERT formula, and you can see why it kind of spells PERT. P stands for principal. We know what that is. E is the number E. R is the interest rate you're getting per year, and T is how many years you're living your money in there. This formula is much simpler than yesterday, PERT. Also, before we do this problem, one thing about the PERT formula, it actually works with exponential growth and like decay. And you're going to see some decay problems tomorrow, like think about half-life problems from biology, same kind of stuff. Okay, this says find the amount of, after 3 years, if $1,000 is invested at a rate of 12% per year. Here's the deal, compounded continuously. When I read that, I know I'm doing PERT. So I know I'm going, okay, A of T equals PERT, okay, P to the RT power. So the principle is what you start with, $1,000. E, the rate is 0.12. The time is years. This is 3 years. Now, if I were you, I would do the multiplication first before I even punch it in my calculator. If you don't, you need to punch it in this way. Make one big parenthesis up here and do 0.12 times 3 in your calc. Punch all that in if you want to do it that way, and you get this right here. You get 1,433.33 cents. And to be honest with you, that's the same problem we did on the video yesterday. I know you don't remember it, but we did that same problem, except we did it with different ends, different numbers. Sometimes we compounded it per year. This would be the most. Compounding continuously is the best, because the more times you compound your money, the interest, the more money you're going to have. So this is the absolute best, all right, or the most for your money. So talk about that some more tomorrow. Can't wait to see you. See you, bye.